Hello, we're Group 12. All members are here. Zongqi, Martin, Chunming, Freddy, Nisari, and Konstantin. Today we will present our project on building an AI trading bot using nature-inspired optimization techniques.
Our project focuses on the development of an AI-powered trading bot for cryptocurrency markets, specifically Bitcoin. Trading bots dominate financial markets, handling up to 70–80% of all trades. We aim to optimize our bot's trading strategies using nature-inspired algorithms that mimic biological or physical processes to solve complex optimization problems.
Our project was divided into two main parts. In the first part, we will review the nature of the nature-inspired algorithms, investigating how they work and which might be suitable for our trading bots optimization. And in the part 2, we designed, implemented, and optimized our trading bots, which use the technique like moving average and MACD signals. Our main focus on this project is how we can build an effective trading bot and how we use different optimization techniques to optimize them.
The trading bot's configuration involves many parameters, from moving average window sizes to signal construction, making it a high-dimensional optimization problem. Manual tuning is not only tedious but ineffective. Therefore, we use adaptive nature-inspired algorithms to automatically find optimal parameters, aiming for better profitability and robustness based on the historical Bitcoin data.
We explored a nature-inspired population-based optimizers and one single-state method, simulated annealing. Each is inspired by a natural phenomenon and has distinct strengths. For example, particle swarm optimization is fast and suited to real-time tasks, while cuckoo search is great at global exploration. Simulated annealing acts as a simple baseline, helping us compare the benefits of more complex optimization algorithms. You can see the main ideas and strengths summarized here in this slide. Next, we'll show you how we built the bot itself.
We implemented all core building blocks from the project specification: standard moving average like SMA, RNA, EMA, and customer filters, triangle, step, Gaussian, random, polynomial, the MACD indicator, time frames, and padding for convolution. We also explore a fully general filter by excluded due to high dimensionality.
The figure shows a side-by-side comparison of filter shapes that we implemented. It visually highlights the differences between the standard moving average like SMA, LMA, EMA, and our experimental filters.
Following the project requirements, we used the Bitcoin historical dataset and split it into two periods, pre-2020 for training and post-2020 for testing. We treat timeframes as a parameter, downsampling from 1 hour to 1 week to a minute to study its effect on performance.
We evaluate the implanted bot building blocks and design the final high and low signals and construct the optimization vector for parameter search. And the next slide will show how we did it.
To keep the project manageable, we first needed to assess the trading relevance of the implemented filters and select a few for optimization. We used the second crossover strategy from the project specification, comparing a responsive weighted moving average to a slower simple moving average with a 10 and 50-day window. Trading was simulated on pre-2020 training data, downsampled to 1 hour, 1 day, and 1 week intervals, with $1,000 initial capital and a 0.03% of transaction fee. The tables show how much money remained after each simulation.
Based on the filters evaluation, we selected the top filters from each table: LMA, SMA, and EMA for optimization.
We tested NACD with the standard 26 EMAs and nitrate signal line using the same trade simulation. On 1 hour data, it made no profit. On 1 day data, it is small loss. On 1 week data, it performed best, growing the portfolio to $1,516.33 $0.02, the highest across all tests, suggesting strong long-term potential and room for turning on shorter timeframes.
Based on our result, we define our high signal as a weighted combination of LMA, SMA, EMA, and MACD, normalized by the total weight.
Following the project's second crossover strategy, we define the LOW signal as a simple moving average with a window size to optimize.
So together, the high and low configurations, along with the selected time frames, define a certain dimensional vector for optimization. Although the structure stays the same, but different optimization methods will explore the solution space differently. So this leading to varied results. And these methods can compare both the parameter effectiveness and the strengths of different searching strategies.
We were interested in nature-inspired algorithms and decided to implement all 6 population-based optimizers, along with the single-state method simulated annealing for a more complete comparison. To keep the presentation short, next we will only show pseudocodes for just 2 algorithms, artificial bee colony and simulated annealing, and explain them briefly in more detail.
The artificial bee colony algorithm simulates a population of bees, employed bees and onlooker bees, searching for good solutions. Each bee tweaks its current solution based on another randomly chosen bee, trying to improve it. If no improvement happens after several attempts, a bee abandons its position and explores a new random solution.
Simulated annealing, in contrast, operates on a single solution. Instead of maintaining a population, it tweaks the current solution slightly and sometimes accepts worse moves, depending on the temperature and the probability. As the temperature decreases, the algorithm becomes less likely to accept worse solutions, focusing more on exploitation.
The quality function are used by all optimizers to evaluate both performance through backtesting. First, we define high and low signals using current parameters. Trading signals are triggered by crossover between the high and low signals. Following the project specification to simulate buying and selling bitcoins, we took initial $1,000 cash and 0.03% transaction fee, and we return how much money left as a quality score for optimizers.
To systematically evaluate the optimizers, we define 5 distinct configurations for each algorithm, varying parameters like population size, iterations, inertia weights, pooling schedules, and other algorithm-specific factors. Each configuration was run independently 10 times to account for randomness and stochastic effects. Training was done on pre-23 data and testing on post-23 data following our dataset split. The goal was not only to optimize trading performance, but also to understand how different algorithms behave under standardized conditions, exploring trade-offs between model expressiveness and search space complexity.
And this table summarizes the outcomes of our experiment across all our optimizer settings. For each run, we calculate the key metrics like the average training and the test profit, the maximum and minimum test profit, and the standard deviation, number of trades, average convenience steps, and the time-free choice on the performance rate, drawdown, and the execution time. To better understand these patterns and explore optimizers' behaviors in more depth, we now turn to visual representation in the next slide.
Convergence shows how quickly each optimizer improves the training profit. In settings 1 and 2, with small populations and many iterations, convergence is slow and gradual, similar to simulated annealing. But in settings 3 to 5, with a larger population, it shows faster and smoother convergence but required more evaluation time. As expected, simulated annealing converges slowly and stochastically by exploring one solution at a time.
As population sizes grow from settings 1 to 5, the average runtime increases. PSO and WOA shows relatively efficient execution, while FA has notably higher runtimes, likely because it uses complex update rules with pairwise firefly comparisons. Simulated annealing remains consistently fast thanks to its single solution nature and fixed 600 evaluation limit.
These plot flows shows the profit distribution across optimizers. CS and WA achieve high profits but with more variability. ABC and PSO deliver more stable but lower profit. GWO is stable but modest, lacking strong exploratory jumps. SA shows high variability, occasionally finding strong solutions but generally less consistent.
The table top 10 max profit shows that CS optimizer dominates across different settings. Also, WA and ABC shows strong results. Interestingly, that CA reached top 10 as well. So it shows us that even simple algorithms sometimes can find strong solution.
The underperformance rate shows how often each optimizer returned profits that were less than $1,000 at the starting rate. ABC shows the lowest underperformance, avoiding poor solutions even with limited populations. However, WA improves with larger populations, and SA underperforms due to its slow, single solution search lacking exploration.
This bar chart shows the timeframes chosen by each optimizer across settings. The PSO, GW, and WA and FA consistently settled at 72 hours time frame, and the ABC and CS sometimes choose longer, like 168 hours frames, suggesting that it maybe get benefit from longer time horizon in some settings. SA randomly picked time frames and adjusted locally, so often get stuck at short 6-hour settings, which means it will perform good enough under the 600 evaluation limit.
Due to the time limit, we won't discuss number of trades, equity and drawdown, and trade signal plots, but the full details and analysis are available in our report.
So in conclusion, in this project, we explored the design and optimization of AI-driven trading bots using nature-inspired algorithms.
We implemented modular bot architecture with moving average MACD signals and adaptive timeframes to create a flexible but manageable hypothesis space.
We tested 6 population-based and 1 single-state algorithms, observing their weaknesses and strengths across different configurations.
Cuckoo Search and ABC consistently achieve strong profits and low risk, demonstrating the power of balanced exploration and exploitation strategy.
In this project, we also reaffirmed that there is no free lunch theory, which means we need to get the balanced exploration and exploitation, means we need to highlight the trade-offs between the accuracy and the computing resources.
Overall, the project provided valuable hands-on experience with algorithmic design, optimization challenges, and experimental evaluation in complex real-world inspired scenarios.
The code, artifacts, and instructions are available on our public GitHub by the link shown in this slide.
Thank you.
Thank you for watching. Bye.